Good morning, everyone. So today we are going to be taking some PowerPoint notes on acidic and basic solutions and how we measure how acidic or how basic a solution is, which is called pH. Okay. While we take notes today, obviously you'll need your notes packet and a pen or pencil. I also need you guys to have out a calculator, and if you're somebody who likes to annotate your notes, get out a highlighter or something that you can use with a different color just to kind of annotate as we go along. All right. All right. So first I want to talk about pure water. Pure water is a neutral solution. And in order to be neutral, that means that there are equal concentrations of hydrogen ions and hydroxide ions. Because the hydrogen ion concentration and hydroxide ion concentration is how we measure how acidic or how basic something is. We'll get into that in a little bit later, but for now, just understand that water is a neutral liquid, and it's neutral because it has equal concentrations of hydrogen and hydroxide ions. Because it's neutral, it has a neutral pH of 7. Okay. Now, in order to have these equal concentrations of hydrogen and hydroxide ions, water does something called self-ionizing. What happens as water self-ionizes is that water is spontaneously forming hydronium ions, that's that H3O plus, and hydroxide ions, the OH minus. So it's constantly and spontaneously forming this H3O plus and OH minus ions from the water molecules. And as it's forming those, it reaches a point of consistency where it has a constant hydronium or H3O plus concentration, and it has a constant hydroxide concentration. When it reaches that point where there's a constant hydronium and a constant hydroxide concentration, that's called equilibrium. Okay, that's what these two back and forth arrows mean. It means that this sample of water has reached equilibrium. Okay. When water reaches equilibrium, there's a constant in chemistry known as the equilibrium constant, or Kw. Kw is equal to the concentration of hydrogen multiplied by the concentration of hydroxide. Okay, so when we have those two concentrations next to one another, oops, hold on guys. When we have those two concentrations next to one another, click the wrong button here. Like here where it says Kw equals HOH, you could rewrite that as Kw equals your concentration of hydrogen multiplied by the concentration of hydroxide. Okay? In water, when water has reached this equilibrium where your hydrogen and hydroxide concentrations are equal to one another, the hydrogen ion concentration is 1 times 10 to the negative 7th. Hydroxide ion concentration is also 1 times 1 to the negative 7th because they're equal. All right, remember up here we talked about the equal concentrations of hydrogen and hydroxide ions. Okay, those equal concentrations are 1 times 10 to the negative 7th. Okay. So once we know those concentrations of each ion, we can calculate the equilibrium constant for water. So we multiply our hydrogen concentration times our hydroxide concentration, and we get, at the end of that calculation, the fact that Kw equals 1.0 times 10 to the negative 14th. Okay, so what does that tell you? That tells you that the equilibrium constant for water is equal to 1.0 times 10 to the negative 14th at 25 degrees Celsius. As long as you understand that we get this number 1 times 1.0 times 10 to the negative 14th, we get that when we multiply the hydrogen times hydroxide concentration, you're good to go. Later in our PowerPoint notes, we're going to kind of unpack this number a little bit, and you're going to see how we use our equilibrium constant in acid and base calculations. But I just wanted to kind of explain where we get that number from. Okay. All right. So in your book notes, you guys also read about something called Le Chatelier's principle. Le Chatelier's principle is a principle that says that if a stress is applied to a system at equilibrium, so if you get a system that's at a constant state in equilibrium and you apply a stress to it, the whole system will shift in the direction that most relieves stress. Okay? This applies in life, and it also applies in chemical reactions. Okay? So when a system that is normally at an equilibrium where everything is balanced, if you stress that system, the system will shift in the direction that most relieves stress. The reason why we talk about this with acids and bases is because acids and bases are determined by ion concentration. Okay? They are determined by the concentration of hydrogen that you have and the concentration of hydroxide that you have. In a solution, if you increase, so in a solution in equilibrium, if you increase the hydrogen ion concentration, the system will respond, okay? And the system responds by reducing the hydroxide concentration. Okay, so those two things are related. Okay, the hydrogen concentration and hydroxide concentration are related. If one increases, the other decreases. Okay. So then the opposite would also be true. If we decrease one, the other will increase. Okay, so that's how Le Chatelier's principle relates to our equilibrium constant in acids and bases. It has to do with when you affect one concentration, so when you increase hydrogen or decrease hydrogen, you will either increase or decrease hydroxide. Okay, now why do we care about that? If we go back to our notes from last week, acids oopsies, computer's thinking here. All right. Acids have hydrogen ions, right? Bases, at least Arrhenius bases, donate hydroxide ions, okay? So if you have an acidic solution, your concentration of hydrogen is going to go up, which would mean the concentration of hydroxide is going to go down. Whereas if you have a basic solution, your concentration of hydroxide will go up, which will mean the concentration of hydrogens will go down. Okay, so that's how Le Chatelier's principle relates to our conversation of acids and bases. Okay. All right, now one more note here about our equilibrium constant before we get into some stuff about pH. Our equilibrium constant will always equal 1.0 times 10 to the negative 14th, okay? If you take some more advanced levels of chemistry, you'll learn about other equilibrium constants. There's one called the Ka. For our class, I just want you guys to be concerned about Kw. And Kw, or the equilibrium constant of water, will always equal 1.0 times 10 to the negative 14th, okay? Because it always equals 1.0 times 10 to the negative 14th, if you know one of these concentrations, so if you know the concentration of hydrogen, or if you know the concentration of hydroxide, you can figure out the other, okay? Because Kw always equals 1 times 10 to the negative 14th. If you know your concentration of hydrogen, all you have to do is plug and chug. You would plug your concentration of hydrogen in there and then solve for your concentration of hydroxide, or vice versa. Okay? All right. So that was all some background information. We talked about, is water acidic or basic? Okay, so we learned that water is neutral. Okay, has a pH of 7 because it has equal concentrations of hydrogen and hydroxide. We talked about this value called Kw, which is the equilibrium constant, okay, which is true for pure water because pure water has equal concentrations of these two ions. We talked about what happens if the concentration of those two ions change. So if you change the concentration of one ion, it will do the inverse change of the concentration of the other ion. So if we increase hydrogen, it will decrease hydroxide. If we increase hydroxide, it will decrease our hydrogen concentrations. That's how Le Chatelier's principle relates to our conversation about acids and bases. Okay. So now we're going to define neutral, acidic, and basic solutions. Neutral solutions are solutions where our hydroxide and hydrogen concentrations are equal. Okay, so neutral solutions occur when our hydrogen and hydroxide concentrations are equal. Okay, so a neutral solution is when those two things are equal. An acidic solution occurs when the hydrogen ion concentration is greater than the hydroxide. So you have more hydrogen than you have hydroxide. Okay? I have more hydrogen and less hydroxide in an acidic solution. Okay? Now in a basic solution, it's the reverse. You're going to have more hydroxide, less hydrogen. Okay? That should make sense using our definition of acids and bases from last week. Acids give hydrogens, bases give hydroxides. So in an acidic solution, you have more hydrogens. In a basic solution, you have more hydroxide. Okay? All right. Now, if these are our definitions for what a neutral, acidic, and basic solution is, we need to have ways of measuring that. All right? So, because in order to define something as an acid or a base, you need to know your hydrogen and hydroxide concentrations. We need to know, how do we measure hydrogen and hydroxide concentrations? And we measure those things with a calculation called pH or pOH. Okay? The pH of a solution is achieved or calculated when here we go. When you take the negative log, okay, so it's important here that it's negative, the negative log of your hydrogen ion concentration. Okay, so we're going to go through a quick practice problem in a minute here, but what I'd like you all to do now is take a second, look at your calculators, and figure out, where is my log button? Okay. On some calculators, it's an actual button that you can just press. On other calculators, you have to use the second key and then press a button, so you might have to look at the little small font above the buttons. But take a few seconds here and find your log button, because you're going to be using it frequently in the next couple days, because you use the log function to calculate the pH of a solution to see how acidic something is. Okay, so below here I've got a quick example for you. It says, what would the pH of a solution with a hydrogen ion concentration of 1 times 10 to the negative 4th be? Okay, so pH equals the negative log of the hydrogen ion concentration. So you're going to plug our H plus concentration into right there. Okay, remembering that there's a negative out front. Okay, you can't forget that. When you do that, what you'll find is that the pH of a solution that has a hydrogen ion concentration of 1 times 10 to the negative fourth gives you a pH of 4. Okay? This formula up here is an important one. You're going to want to make sure you memorize that one. Okay? You need to know that the pH of a solution is the negative log of the hydrogen concentration. Okay? Now, this formula will tell you how acidic something is. Okay, pH expresses acidity. All right. Well, if pH expresses acidity, pOH is going to be the opposite. pOH is the calculation that expresses acidity or alkalinity. Alkalinity and basicity are two different words that mean the same thing. It means how basic something is. Okay. So let's go ahead and do another quick example problem here. It says a solution with a hydroxide concentration of 6.7 times 10 to the negative 11th has a pOH of, okay, so here you're going to plug your hydroxide concentration in to your formula. So pOH equals the negative log of 6.7 times 10 to the negative 11th. Okay, plug that into your calculators. You'll find that this particular solution has a pOH of 10.2. Okay, however, pOH is not a calculation that we typically use to tell how acidic or how basic something is. You have to take one more step to tell me how acidic or how basic something is, okay? And what you got to do is you take 14 and subtract your pOH from it. The reason why you do that is because we use a pH scale to tell us how acidic or how basic something is. And then we use this equation or relationship to figure out, all right, if this is my pOH, okay, and in order to know how acidic or how basic something is, I have to know the pH. The pOH does not tell me how acidic or how basic something is. To know how acidic or how basic it is, I have to know the pH. So for this particular example problem, what we need to do is we need to take it one more step and solve for the pH, because then the pH will tell us, like I said, how acidic or how basic it is. So then we plug our pOH into this problem, and we find that this solution has a pH of 3.8, which is pretty acidic. Okay. All right. So on your paper, what we're going to talk about next is the pH scale. Okay. Now the pH scale goes from 0 to 14. Okay. And on that scale, 0 to 6.9 is acidic. Okay, so what I'd like you guys to do on your notes, okay, you guys have this on your notes as the scale. I want you to write in where the acidic pHs are. So where it goes from 1 or 0 all the way just before 7, I want you to write in that that's acidic. Okay, and then along that line, you can include any of these examples by the pHs of those different things. Okay, so battery acid has a pH of 0, so you could write battery acid by 0. Black coffee has a pH of 5, so you could, next to pH 5, you could write black coffee. Your stomach acid has a pH of 2. Okay, that's why people who have like repetitive vomiting issues will oftentimes have tooth erosion, because that stomach acid will actually like erode the enamel of their teeth because it's so acidic. So those are acidic pHs. Neutral is 7. Everybody, I want you to label 7 as neutral. Okay. And then as you go to the right there, pHs of 7.1 or higher so 7.1 to 14, those are all basic solutions, okay? So I'd like you to include a couple examples of basic things as well. So baking soda has a pH of roughly 9. Household ammonia, which is like household cleaner. Windex has ammonia in it that has a pH of 12, so that's a very basic solution. Oven cleaner or drain cleaner like Drano is extremely basic. That's why it's pretty dangerous. You don't want to mess with it. Has a pH of 14. All right. So one thing I will point out to you about all these different examples we've gone over, most of them, with the exception of battery acid, are relatively common household items. So you can find common household items that are super acidic or really, really basic throughout your house. So it's not a crazy thing to have something that's really acidic or really basic hanging out around your house. Okay. All right. So this relationship is one that we were just talking about a second ago. It's the relationship between pH and pOH. So pH and pOH will always equal 14 when added together. The reason for that relationship gets back at some of the background information we talked about earlier. The fact that our equilibrium constant of water is always equal to 1.0 times 10 to the negative 14th. How that's related, we're not going to get into the nitty-gritty of it. What I just want you guys to know and remember and memorize is the fact that pH plus pOH always equals 14. Okay, so that's why earlier when we calculated the pOH of our solution, in order to know the pH of our solution, so how acidic or how basic it is, we had to subtract the pOH from 14 to get that. This is why. Okay, there's another example just below down here. If you take a look just beneath here, it says that if a solution has a pH of 6.7 and a pH, or I'm sorry, what this is supposed to say is if a solution has a pH of 6.7, what is the pOH? Okay, so if we solve that by plugging in our numbers in the equation above, what this is saying is if your solution has a pH of 6.7 and you're solving for your pOH, you would subtract 6.7 from either side and eventually solve for the fact that you'd have a pOH of 7.3. Okay? Almost done here, guys. All right. So now we're going to get into some of the practice calculations. This is getting a little bit long, so we're going to try and go through some of it quickly. All right, we're going to pause a couple times here to let you get a breather and practice some of the calculations yourself. But what I want you to do now, I want you to, with a partner, go through the next 3 practice calculations. So I want you to do the 2 calculating pH problems as well as the calculating pH from the concentration of hydroxide. Work together. You can work with your partner. You can work in your quad squad. Take about 2 to 3 minutes to try and do as much of this as you can, and then we're going to go through the answers together momentarily, okay? And then okay, guys, so that was a lot of notes. That was 23 minutes. Rather than going through the answers to these practice problems together now, what I'm going to have you do is attempt to finish the rest of the practice problems. The only ones that you would have a little bit of trouble doing that for would be the calculating the hydronium concentration and hydroxide concentration from pH. So that would be on the back of, or I'm sorry, on the front of the second page. So I want you guys just to turn there. Okay. So for these ones, what you guys are going to be doing is essentially working backwards. So here you're going to be calculating pH and POH from the concentrations for hydronium or hydroxide, okay? In order to do that, you use these two formulas. These two formulas, as well as the negative log of your hydronium or your hydroxide concentration, are essentially opposite formulas of one another. Again, the math behind it, I'm not going to get too detailed into, but just know that they're related again. But you would use these if you were given a problem like this, okay, where if I gave you the pH of a solution, pH is 6.4, and I asked you what is the concentration of hydrogen or hydronium, okay? So this is a way to work backwards to go from pH to concentration, whereas the log formula that I gave you before is a way to go from concentration to pH. Okay, so go ahead and fill those two blanks in on your note packet. With the rest of the time that you have in class, I want you to attempt to finish these practice problems, get as far as possible, okay? And then we are going to discuss these practice problems tomorrow when you guys get to class, all right? I know these note days are long, and I know it's hard that I can't answer questions for you, but hold on, let me get this back. If it's challenging to do these practice problems without being able to ask me questions, what I want you guys to do instead would be to write down some of your questions that you have from your notes today, okay? So that tomorrow when I come back to school, we can talk about what areas are confusing still, and we can maybe hash those out a little bit together tomorrow. Alrighty? You guys have a wonderful rest of your Tuesday, and I will see you when I get back to school tomorrow. Adios for now.